Hello, everybody. Welcome to the Long Range Colloquium. My name is Giulia Pacchioni, and I am an editor at Nature Reviews Materials, and I will be your host and moderator today. I would like to welcome you here on behalf of the Virtual Science Forum. And if you are not familiar with us, the Virtual Science Forum is a team of physicists developing a free virtual conference initiative to support online events. And if anybody is interested in joining us and helping with the long range colloquium or has ideas for other events they want to organize, we would be very happy to hear from you. And I'm popping a few links in the chat where you can find our website and Twitter and GitHub repository. So first of all, I would like to thank the institutional support that makes it possible to continue this work, and in particular, the Kavli Institute of Nanoscience Delft. And now a couple of technical details. You're very welcome to ask questions during the talk if you wish, or there will be plenty of time at the end. And if you want to ask anything, please raise your hand using the button at the bottom of the participants panel. So I can see you have a question and I will find a good time to interrupt Deji, and I will unmute you so that you can ask your question. And please note that the talk is being recorded. So it's time to get started. It is a pleasure to introduce today's speaker, Deji Akinwande from the University of Texas in Austin. Deji's research focuses on 2D materials and nanomaterials and on the translation of devices made of these materials from the lab towards application, which is, I think, a very exciting topic that I hope we will hear a lot about tonight. We are very much looking forward to your talk, Deji. So please go ahead, share your screen, and we can get started.
Okay, very well. So it's my pleasure to be connected with all of you today. This is my first time really learning about this virtual science forum, and I'm sure it's not going to be the last time. I look forward to also joining for other talks in the near future. So I'd like to thank the organizers for inviting me and bringing this forum to my attention. And based on what I was told was the major, the background of most of those attending this forum, I decided to focus my talk more on some of the more physics, device physics relevant aspect of my research. So for the sake of time, I won't go into a lot of details, but feel free to ask questions should you find details lacking in any particular slide. I'm really mostly going to be talking about atoms to device science and a little bit about applications towards the end. This talk will mostly focus on 2D nanomaterials, as Julia mentioned earlier. And my email is at the bottom. You're always welcome to email me or check my website and engage on further topics. So in a nutshell, the research in my lab at the University of Texas, let me select the laser pointer, really spans materials, science, and electronics. As was mentioned, we're mostly very focused on taking laboratory discoveries or ideas and conducting research and development towards applications, scientific applications of those ideas for technology. So I have students from all over the place and researchers from all with different backgrounds that contribute in material science, electronics, and device physics. So today I'm mostly going to be talking about memory devices, the science and technology and applications of memory devices. So just to give you a very brief history, especially since the audience has such a broad background, electronic technology since the very early days of the last century, they've mostly been driven by a single primary device, dominant device. So 100 years ago, that was vacuum tubes was the dominant device driving the electronic industry. And then for many decades, there was a strong interest in solid state because vacuum tubes operate with principles of charge and ion transport in vacuum, so they consume space. So there was a very strong interest in solid state devices. So the first primary device that in that era were diodes, so PN junction diodes, really was the nascent technology that drove the semiconductor technology. And then they were dominant for many decades until the 1960s, when transistors were invented and commercialized at Bell Labs. So transistor became, especially the field effect transistor, became the dominant driver for the semiconductor technology up until about a decade ago. Since 2010, memory devices have become the technology driver for semiconductors and electronics. And that is very, very obvious to everyone. If you want to buy a new smartphone with 256 gigabytes compared to 512 gigabytes, you're going to pay hundreds of dollars or pounds extra just for that more memory capacity. So within the memory space, there's actually very, very rich wealth of physics. Some people say more interesting than transistors, because you can make a memory device from a variety of phenomena. The flash-based memory, which is what you have in your USB sticks and your solid-state memory in your computers, those are based on charge trapping. So it's mostly about charge physics. Then you have ferroelectric memory, which is based on spin physics. You have phase change memory, which is based on thermal physics, how you can control heat in a way to change the structure of a material from amorphous to crystalline. So then that results in different resistances of that material. And then you have ionic-based memory. So two kinds of those are solid electrolytes, where metal ions can suddenly diffuse into a solid electrolyte, or metal oxides, where you have vacancy ions that exist within an oxide. And in all of these cases, the main modality is you're measuring or you're observing a change in the resistance of this device as this phenomena emerges. So the last two, or maybe even three, are colloquially known as memristors. So of course, I know many people are familiar with this. Some of you may have heard this. So memristors are really jargon for these last two kinds of memory device. So let me use this one slide to perhaps explain the basic physics at the very elementary level. So these memory devices, especially the last two, which will be the focus of my talk, memristors. So those devices are metal insulator, metal type of device structures. They're MIM, or you could say a capacitor structure. And of course, the insulator is non-conducting. So if you try to measure current flowing from the top electrode, which the top metal, to the bottom electrode, there you see virtually zero current. So we say this is an off state, and it's a high resistance state. So even though you may have defects, these defects themselves may conduct, but because they don't create a path for current to flow, the device is off. Now, then the other state of the memory is when it's on. So then this is very, very similar. The best analogy I like to give is that of the lightning effect. So if you think, for example, as the top electrode is, you say the sky, the insulator is the air, and the bottom electrode is the earth. Of course, we don't walk around every day with, current flowing from the sky to the earth. But during lightning, which is a high voltage phenomena, the lightning is ionizes, the high voltage ionizes the air, and then you could have this filamentary one-dimensional current flowing from the sky to the earth. So the memory effect, or the switching from the off state to the on state, is very, very similar to lightning at the nanoscale in solid materials. So you apply a high voltage commensurate with the thickness of the dielectric, and then if it's sufficiently high, you have a partial breakdown of the material, or you could say ionization of the material. So in the case of metal oxides, you have oxygen debonded from its bonds to the metal, and then it leaves behind in its wake these oxygen vacancies. These are charge states that can align, and then they form this one-dimensional filament, just like lightning. So if you then do a measurement of current versus voltage across this sandwich, suddenly there's a current flowing. So we call this the on state. And unlike lightning, thankfully, you can actually reset this process and recycle it. In the original papers, it was a few hundred times, but nowadays you can do millions of times. In the most optimized devices, you could even do billions of cycles. So very, very interesting application of defect. So all is good, but there's some challenges. So for many years now, there's been great interest to reduce the size. In solid state devices, generally, we're always trying to reduce the size for obvious reasons. Those reasons include, if you can make these devices smaller, you can get higher density. Everybody will appreciate that, getting a 1 terabyte USB at a low cost is better than having a 256 gigabytes. It's forming free, so that's a performance issue. It's going to consume lower energy. You have less matter to deal with. And it's going to be a switch. The switching time will be faster because the length scale, if you make them smaller, especially the thickness, is going to be shorter. However, there's been challenges that have prevented this scaling, at least in metal oxides. So these challenges include the fact that as you make them smaller, these defects, the native defects in the material, for example, in many oxides, begin to form a short between the top and bottom electrode. So that leads to very high leakage current, lower on-off ratio. And the fundamental scientific reason is because these oxides or solid electrolytes used in these memristors are disordered materials. So there's just a lot of defects. When it's thick, it doesn't matter, it can still function, but when it's very thin, these defects dominate and you cannot control the phenomena. So that's exactly where I came into the picture. I said, voila, I work in 2D materials. These are atomically thin materials, so they should be able to allow the thickness scaling of these memory devices to less than a nanometer, a single atomic sheet. So, most of you are familiar with 2D materials, but for those not, graphite is the most popular system, where if you think of it as a stack of paper, you can peel a single layer of carbon atoms from the graphite, and that's the so-called graphene. So it's exactly the same reason why pencil functions like pencil. HBN is an insulating analog of graphene. Again, you can peel a single layer and you get a monolayer insulator, very, very thin. And then you have other materials like MOS2, which you can peel monolayer from the molybdenite crystal, and you get a single layer. And depending on who you speak to, there are hundreds or thousands of these 2D materials. So very, very rich space for science and engineering. And if one could use these 2D materials for this memristor, you could form this so-called crossbar. So this is the typical configuration in high density information storage today. And you could make the entire crossbar less than 1 nanometer because the 2D materials is very thin. You could select your choice of materials from the portfolio, metals, semiconductors, dielectrics, whatever you want. You could control the defect density by orders of magnitude, unlike metal oxides where you get what you get. In this 2D materials, they're crystalline materials, so one can engineer the defects at pleasure. And it's very scalable, so it's easier. You can get the densities that exceed the connections in the brain. So the brain connections are one of the most, there are more connections in the brain than there are stars in the universe. So the brain is actually highly connected. But with this 2D materials, you can exceed the connection needed for brain for brain computing. The energy will be very small, so I'll show some results towards the end, where we're now in the zetajoules. Thermal energy at room temperature is 4 zetajoules, so we're approaching this limit. And then, as I mentioned, the time scale is also much shorter. So when we started this research about 5 years ago, I was doing my sabbatical at Cambridge and looking for new ideas, which is what one does during a sabbatical leave. I was beginning to think, okay, maybe I can contribute new idea of using 2D materials in memristors. Up until then, this had not been realized before. And the popular opinion was that just like in metal oxides, there was a lot of suspicion that the current leakage through this very, very thin 2D material will be excessive and this would not work. Indeed, the only paper at that time was by my very esteemed colleague at Northwestern, Professor Mark Hersam, where he showed a lateral device, so a planar device. In this case, you could use a third terminal, like in a transistor structure. This is now called a MEM transistor, where it's a memory device, and the third terminal can be used to modulate the memory performance. So this is attractive for some applications, but it lacks the density capability of the vertical memristor because the lateral devices always take orders and orders of magnitude more space. Scientifically speaking, this memory effect in the planar device requires certain grain boundaries in a polycrystalline film. So we actually tried to make this. It was very difficult for my student because we could not reproduce that kind of favorable grain boundary. So my student was now graduated a few months ago, Rui Jing. Last paper is actually coming out in Advanced Materials in 2 weeks from now. She said, okay, why don't we return to this idea that, is suspected to not work, and let's just give it a try. You have to keep in mind, Rui Jing was a very special student of mine, and special in more than one ways. And one way she was special is she was very, very close to boyfriend who, for practical purposes, we can say they're going to be getting married shortly. And so they wanted to work together on the same project. He works on memory. So she felt if she could work on memory, they could publish papers together, they could be in the lab together, they could discuss ideas together. They're that kind of a couple, unlike maybe some other couples. So I said, okay, no problem, go and give it a shot. I always encourage my first year students, even my second year students, to try any idea that they choose, because in America, the PhD takes 5 or 6 years. So if you waste, 2 or 3 years with no results, it's not the end of the world. You still have another 3 years left to get a PhD, so which is abundant time to still get results. So lo and behold, Rui Jing was actually very successful. After 6 months, she showed fantastic results. This is a monolayer of MOS2 between 2 gold electrodes. We use gold to rule out metal oxides that can form for non-noble metals and that could also produce memory effect. So we had to stick to noble metals. And then you see this normal, these are characteristic electrical current versus voltage curves of these vertical structures. At very low voltage, or initially it's very low current, that's the high resistance state, let's say binary 0, and then around 1 volt, corresponding roughly to electrical fields of 1 volt per nanometer, you suddenly have the switching effect where the current jumps. So then you get a high current regime or low resistance regime. So we call that the low resistance state. So this is non-volatile, which means if you turn off the power, it's going to stay in the last state that it was. So if it was in a high resistance state, the blue curve here, if you turn off the power, you keep measuring the resistance or current for weeks and weeks. This is a week-long measurement. It's going to stay in that state. If it was in the high current state, the red data here, again, it will stay in that state. So it remembers the last state and stays there until it's reset. To reset it, then one has to apply a negative.
May I ask a question? So you mentioned that this was gold on both sides. Can you explain what gives you the asymmetry so that putting on a positive voltage gives you turns it on and putting negative voltage turns it off, or do I misinterpret the loop?
Yes, so David, that's a very good question. I'm actually delighted to see you. If you may recall, I took one of your classes when I was a graduate student at Stanford. So yes, that's a very good question. So our current thinking is that even though the elemental material is the same on both sides, the geometry of the material is not the same on both sides. And I'll speak more about that when I talk about the mechanism. So the geometry on the top side is a deposited gold film. The geometry on the bottom side is actually, in this initial result, is a gold foil. So I think these differences in geometry may play a role, but the fact of the matter is we don't have an exact answer to that question. We just have, we have an hypothesis to explain it.
Thanks very much.
So one of the criticism that we received in the early days, 4 or 5 years ago, was that, since we're reporting this for the first time, there was a lot of suspicion that maybe, this was extraneous results, not intrinsic to the material. So we decided to get this MOS2 materials from other experts that grow high quality materials. So basically on the list here is virtually every kind of MOS2 that can be produced. And we could conclude that this phenomena exists in all of these materials. So we declare then that this is an intrinsic effect to the material. So as part of the criticism that we received, we went through great effort to make very clean samples. As all of you know that do experiments, when you make samples with lithography, you have contamination. So those contaminants could play a role, and that is a very fair argument. So we said, well, let's make very clean samples. So these are what we call lithography-free, transfer-free, going back to the question that David mentioned. So these are MOS2 materials that can be grown directly on gold foil. Nowadays, you can also grow them on gold film. And then you can use a shadow mask to deposit a top electrode so that there is no polymer or lithography process involved. So it's as clean as you can get. So we see the same phenomena really in this. This is a little bit more symmetric than the others. And then another concern that we got was that this may be sharing the same physics similar to what Mark Herson published in his lateral device, that grain boundaries may be playing a role. So we went through significant effort to make devices on single crystal. As those of you doing experiments know, you can grow these almost perfect triangles of MOS2 that could be large enough, and then one can deposit a top electrode on top of that. And then, again, we see, this emergence of memory effect. And of course, one doesn't need to be a genius to realize that, well, other electrodes may work. There's nothing specifically special about gold. So we've tried silver, graphene, copper, nickel, and a variety of electrodes. Their performances are a little bit different, but more or less they all function successfully. So this is the kind of performance data. If you're an electrical engineer trying to commercialize device technology, this is the data that you care about. So the endurance means how many times can you cycle this? I mentioned earlier that in modern devices, emerging memory, it can be cycled billions of cycles. So this is still early stages. We don't actually have the testing capability to do proper cycling tests. So these are DC endurance instead of the desirable pulse testing. Nonetheless, we can get hundreds of cycles. So this is not something that is not repeatable. It's very repeatable. Retention, I mentioned earlier, it remains in that state at room temperature under ambient conditions. It's very low energy. This is actually very, very nice results we just got with our collaborator, Elam Yalon from Technion in Israel, where they have very advanced test time domain testing capability. So we can now switch this states, using pulses less than 500 picoseconds. The energies are in the picojoules, so it's very, very energy efficient. And of course, everybody knows that works in the space that 2D materials are essentially scaffolds that are flexible. So you can put this on Kapton or any substrate. You can bend it until you're tired, and it's still quite robust. So, just a little thinking over a cup of coffee, then one can quickly realize, well, if it works for MOS2, why shouldn't it work for the other TMD materials? So indeed, this is exactly what the experiments we've done. So we tried all the transitional metal sulfides that we could get our hands on. Some of them are from collaborators, and we're very grateful for them. And so you see MOS2, WS2, there are differences in the switching voltage and currents, but mostly this is to highlight that this may be a universal effect. We call it atomristors just, as a, jargon, colloquial jargon, as it's a memristor effect in atomically thin films. So we call it atomristors. Transitional metal selenides, also all the samples we could get get a hold of, we also saw this effect. And then the other materials, I would like to point out that heterostructures show this effect as well. And then the thinnest of them all is HBN. So one layer HBN, 0.3 nanometer active layer also shows this effect. I see maybe there may be questions in the chat. Perhaps I should pause for a moment.
I don't see any questions yet.
Oh, okay. Anybody wants to ask a question at the moment? I'm happy to pause and have a drink. Okay, very well. So I'll just proceed. So of course, this year, the list here is about a dozen materials. We hypothesize that this is universal and may exist in all the non-conducting 2D layers that one can envision. So now let me go to some of the physics mechanism behind this. So one of the early criticism that we received from our colleagues, which is a very fair thing to receive criticism in scientific research, it's actually necessary. Um, one of the criticism that we received was that the current densities, if you look at some of these current densities in the off state, they were just unusually low and very dissatisfying to people that study like transport across interfaces. That how come it's so low, the current flowing through an atomically thin barrier? And if you actually did the model, and the most popular model that many people use analytically is the WKB approach. If you use this approach and try to model the current in the off state, you're going to be off by 2 orders of magnitude. The model is going to predict currents that are 2 orders higher than some of our lowest currents. So this actually puzzled me, and I couldn't come up with a good explanation to answer this criticism. So finally I said, okay, let me actually go and read the original paper. So I think the most popular paper that people cite is the one by John Simmons, the Canadian. And he described the WKB as a theory for studying transport across an insulator where you have metal on both sides. Exactly the kind of structures we're looking at here, MIM. And the fantastic thing that I saw when I first started reading this paper is that John Simmons mentions in the very first paragraph that, oh, by the way, this theory does not apply for barriers, or it breaks down for barriers less than 1 nanometer. So if you have an insulating barrier that's less than 1 nanometer, the theory begins to collapse because this WKB, or this triangulation of the barrier, collapses because you're neglecting dielectric constant effects, you're neglecting image force correction effects. All these effects that don't play a role if the barrier is thick becomes very dominant when the barrier is less than 1 nanometer. So that is one reason that we could identify. And then the other reason which John Simmons did not recognize, and you cannot fault him for this, was that this theory, and in those days, they were dealing with epitaxial interfaces. So intimate interfaces between insulating barrier and metal. And so in the case of the 2D material, this is not the right picture. The actual picture is you indeed have a van der Waals gap between the material and the metal. So it's not an epitaxial interface. So what that means is when you're applying theory to model these devices, you have to take into account these additional tunnel barriers. Indeed, there are now several papers that have estimated what this gap is for different metal combinations with different TMDs. In the case of MOS2 with gold, this gap, the sum of the top and bottom gap is actually commensurate with the thickness of the material. So it's a non-negligible gap. So when you take into account this gap, this correction effects, you can now actually begin to get the kind of current densities that we observe in this monolayer sandwich between metal. So we became satisfied that this could be explained. The other criticism, indeed, when we first submitted this to Nature Nano, the main criticism for the reviewer was we didn't understand the mechanism, which was a very fair feedback because we're just dealing with results and it takes a while to get to the mechanism. So 2 years later, after we received that feedback report, I realized the only way to fully understand the mechanism is by doing experiments. The best way to do experiment is by using STM, because with the STM platform, then you could do spectroscopy, you could do imaging, and you can actually also do transport. Unfortunately, I am not an STM person, but I was clever enough to recognize that if I could only hire a very good STM postdoc, I may be able to address this problem. So money fortunately fell from the sky, and as my luck began to shine, I gave a talk at Oak Ridge National Lab And one of the directors of the lab said, oh, by the way, I have a postdoc leaving. He's our top STM specialist. If you want to recruit him, I would highly recommend, and he can return to Oak Ridge and be permanently stationed as a member of your group. So I said, voila, that is a great idea. So I hired Seban, who is an STM specialist. He helped build the multi-probe STM station at the Oak Ridge CNMS. So the idea then is to, we had an hypothesis that defects was playing a role. So we said, okay, let's image the MOS2 material, find clean areas like this, and find areas that have defects. So these defects here are sulfur vacancies. And then we said, okay, why don't we now use the nanoscale resolution of the STM tip, sub-nanometer in this particular case, and park it in the clean region and do transport. So if you do transport, what you see is you see a kind of diode-like, nothing extraordinary, asymmetric curve. So in this particular case, again, there's an asymmetry. This MOS2 is sitting on a gold film. The STM is a gold tip. Even though the elements are the same, the geometry is different. So you would normally expect some asymmetry in the IV curves. Then we said, okay, why don't you now put the tip and park it on top of a defect, any defect, and then park it there and do transport measurements. And then if you do that, you begin to see the emergence of memory effect. This windows in the IV curve is reflective of memristor behavior. So we could conclude that defects, in this particular case, single vacancy defect or di-vacancy sulfur defect, are essential, but it turns out that they are not enough to get the memory effect. You need an additional ingredient. So in the course of his experiment at the Oak Ridge lab, he was able to do very, very advanced measurements. So I'll show you now the set of experiments that took at least 2 years to complete. So this is a schematic, and here we have an STM image. This image is mostly focused to do transport. So we've identified here a sulfur vacancy, and in the paper we'll provide details to establish that this is a sulfur. In this particular case, it's a sulfur di-vacancy. So the sulfur on top and the sulfur below a metal atom is missing in the MOS2. So that's a very, very, very energetically favorable defect in this material. So now, after imaging, you can now go back to the same spot and do transport. So you apply voltage. So these are not normal spectroscopy. These are transport measurements. So tip is actually touching the material. So you can apply high voltage. You can switch from the off state to the on state. And then the hypothesis then is that the gold atom is going to be bonded, is going to be adsorbed and bond to that vacancy. To prove that, he now goes and does imaging exactly at the same spot. And then we see a bump in the place where the defect, the vacancy was presently. So we've done analysis, the geometry of the bump correlated with calculations, DFT calculations. We conclude that actually this is a gold atom sitting on this vacancy. Then it can apply the reverse voltage to turn it off or reset it. And then you see around 1.1 negative voltage, it goes back to its initial state. So the hypothesis then is that we had was that the gold will be debonded from that site. To prove it, he does imaging exactly after, and then we can see that indeed the vacancy has recovered. The gold atom is no longer present in this vacancy. So Seban did spectroscopy. Of course, you can also do the STM in the same positions. It did spectroscopy, and this I think really concludes the mechanism. So if you do spectroscopy, of course, it's a semiconductor. So you have a region that doesn't conduct in a pristine material. DFT calculations. And then for a single sulfur vacancy, the vacancy itself is not conductive. So again, that's the black curve here. The vacancy does not conduct, and that agrees well with DFT calculations. So we have simulated images, we have experimental images, but metal atom adsorb onto this vacancy conduct. So if you look at the spectroscopy, you can clearly see conducting density of states, and this correlates well again with DFT calculations. So the bottom line in terms of the mechanism is you have metal atom. In this particular case, it's gold, but it could be a variety of metal ions. They can favorably adsorb onto the vacancy. They're very stable, but they can be debonded by reverse voltage subsequently. And this thing can repeat itself over and over again. And he did this in the STM, I think 3 or 4 cycles. Of course, the STM is not a platform for doing repeatability measurements, but 3 or 4 times he could actually observe this effect. So
I have a question, Deji.
Yes.
I'm curious to know if when you go on the vacancy and you do your voltage sweep, do you get a gold atom every time, or sometimes you get the effect and sometimes you don't?
So yes, Julia, that's a very good question. It's not every time. So I think according to statistics, it's about, let's say, 1/3 of the time.
Okay, that's quite a lot.
Yeah, so it's about 1/3 of the time. So the majority of times, actually, if you do a high voltage transport, we don't see the effect. So there's still some, trigger, phenomena that we don't understand why we see it in some cases, why we don't see it in other cases.
But on the other hand, I would imagine when you're trying to get rid of the gold atom, that is more predictable. I would think it's easier to pick it out.
Yes, if the effect is there, if gold atom is adsorbed, you can definitely and 100% of the time recover the gold. And this effect, we only see it in defective areas. In the pristine areas, hundreds of measurements, you will not see the memory effect. So you need defect, and you need metal ion adsorb into the defect to get this memory effect.
Yeah, thank you.
And we've done the same thing for HBN. I won't belabor you with the same understanding, but it's more or less the same physics for HBN. So since ultimately I'm an engineer, I feel obliged to speak about applications. So even though this is an atomic effect that you can trace down to a single atom, there are macroscopic applications of great interest. So one of them, and perhaps the biggest application for all memory devices, for information storage. And so one criteria for that is to have high repeatability, to be able to cycle this not hundreds of times, but preferably millions and billions of times. So there's been progress towards that end. Feng Miao's group in Nanjing, who I visited last year, has shown that by doing some chemistry, in particular, small oxidation of the MOS2, you can improve the endurance of this effect, how many times you can cycle it, from hundreds to millions. So we're trying to apply now this idea to monolayer films. And then very nice work towards this end was also shown by my very esteemed colleague at Purdue, Jörg Appenzell, who showed that besides this phenomena that I described, another phenomena also exists in certain 2D materials. In this particular case, this is MOT2 received from NIST, from Sergey's group. And what they claim to be the responsible physics is that in a normal 2H phase of the MOT2, you have this very nice van der Waals gap between the different layers, but under high voltage, you have some sort of phase change where it goes from this 2H to some kind of disordered 2H prime, where suddenly this van der Waals gap, according to cross-sectional TEM, doesn't look so clear. There seems to be some sort of interaction between the gaps. So anyway, there's a great interest to better understand this phenomena as well in terms of this, quasi phase change phenomena in certain 2D layers. Neuromorphic computing is very important. This is the computing that tries to emulate the brain. The main idea is instead of having memory states that are digital, that means high memory, low memory resistance, you need memory states that are analog. You need to be able to program the resistance over a range to emulate the synaptic weight of connections in the brain. So we're very delighted to see this work by Don-Hee Ham's group at Harvard, collaboration with Samsung, because they were the first to reproduce our device structure. So, you always wonder if others can reproduce your work. So I was extremely thrilled, even though I had absolutely no interaction with them. They independently made similar devices a few years after us, and they showed nice data. They use copper in this case instead of a symmetric structure, because copper, they claim, is a lower energy. So switching voltages are, just, not far from thermal energy, about 0.2 volts. And they could program the resistance states. I won't talk too much about this, but you want to be able to program the resistance states increasingly. So that's potential. That's called potentiation. You want to be able to program them also in a decreasing, with a decreasing slope. That's called depression. These characteristics are critical for the neuromorphic applications. Then again, I won't dwell too much on this, but recent collaboration between Mario Lanza, myself, and others, we showed wafer scale using HBN in this particular case, wafer scale neuromorphic computing, and we could show 25 programmable resistance states. The point I just want to emphasize is in these devices, we could get switching energies of around 100 zetajoules. So this is the lowest switching energy reported so far. So we're just 30 times above KT. So very, very interesting for the energy efficient computing platforms. What I'll probably spend 2 or 3 slides on just to wrap up is applications. I'll talk about switches. So our sponsors, they came to us and said, okay, great, you've discovered this memory phenomena in 2D monolayers, but can you tell us a new application? We don't, it's great that you have existing applications, but what about new applications? That's easier to commercialize. So I started thinking, what new application can we possibly think of? So I was very fortunate to go to a Northrop Grumman workshop where they invited a bunch of us to discuss new ideas. And as part of their new research and development initiative a few years ago, and one of the outcomes of that was a collaboration with Northrop Grumman called Northrop Grumman Next. I don't know if it's still active now, but we came to learn these switches may be very good for radio frequency and RF switches. So 5G, of course, everyone is familiar with this now, spans from the gigahertz to about 100 gigahertz. It's of great interest for many technologies, including artificial intelligence, where you want to connect everything to the cloud, you want to have access to real-time data. So it's very important that switches that toggle between all those different bands, 4G, 5G, LTE, Bluetooth, millimeter wave, RF, all of these bands need switches to toggle in real time. So if you're a cell phone tower, it's not a big deal. You're connected to the power supply. But if you're in agriculture, using sensors, mobile health, smart devices, you need very low power switches in order to function and connect to the cloud. So today's switches are transistor switches that consume incredible amounts of power, because not only are they consuming power when you switch them, they're consuming power when they're idle. So using memory as switches then becomes very interesting. So these are so-called zero power, zero DC power, because the static power consumption is 0, and it only consumes power when it's switching from one resistance state to another state. So that is well understood. What was not applicable is that the conventional emergent memory, like atomristors, metal oxide, conductive bridge RAM, all of them, their resistances are too high to be useful for radio frequency or 5G. The requirements are you need to be less than 50 ohms, because that's the standard resistance for radio frequency systems. So in general, you want to be less than 10 ohms. And when it's off state, you want to be much greater than 50 ohms. So let's say something above a kilo ohm. In the off state, it also behaves like a capacitor. So you want that capacitance to be, let's say, less than 10 femtofarad. So altogether, for the radio frequency or 5G switches, you need this figure of merit, which is more or less an RC time constant. It needs to be greater than terahertz or less than picosecond to be interesting. So I won't spend too much time, because these are more specialist data, but those that do radio frequency measurements will be familiar with these so-called scattering parameters, which is just a measurement of the loss. So if you had a perfect transmission line, it's going to be 0 dB as a function of frequency. So in this particular device, in the on state, it's very close to 0 dB. Anything better than negative 0.5 is actually very good. So it can actually now operate with the most recent data with our French specialists. They have measured this actually up to 500 gigahertz. So the insertion loss is very good. We're now classifying it as 6G, because 6G is 100 gigahertz to 1 terahertz. So it's now suitable for 6G applications for the next decade. Then in the off state, again, the same scattering parameters. In this case, we call it isolation. You want it to be less than minus 15 dB. So in this case, we're around minus 30 dB worst case. And so this is very, very good. So these are record numbers, even though this is a relatively nascent device. And we've done this with MOS2. MOS2 is a relatively small bandgap material, so it cannot handle a lot of high power. So we went to some sponsors and we said, oh, could you give us funding to support further research? They said, hey, the MOS2, the power levels that you're observing, which is 10 dBm is the maximum power, that's not good enough for many applications. Could you get to higher power? We said, okay, if you give us sponsorship, we'll do the research to higher power. How can you get to higher power? Well, switch the material. So HBN is a much more, thermally stable material. It has a higher band gap. It can endure higher temperature. It has greater oxidation resistance because when you send high power through these materials, the local hotspot can be much higher than the ambient. So oxidation effects cannot be ruled out. So HBN is more attractive for this. So we did the same experiments with HBN. I won't go through the RF data. It's similar to the MOS2, but it can handle more power. So this is the output power versus input power. So for transceivers, when you're sending signals from, let's say, your smart device to the other devices, you need to be able to send high power because that signal needs to travel a great distance. So 20 dBm is what we can achieve with HBN, which is 10 times more than the power handling than MOS2. So for the sake of time, I'll skip some of this. This is just to show that we can actually measure the hotspot temperature using infrared camera on a working device as a function of the power input. So you can see the hotspot develops where the device is located, which is the middle of the bow tie region. And to cool it off, the best thing is to put it on a diamond substrate. So all the devices now that we make are on diamond substrates because of the thermal conductivity of diamond compared to silicon oxide.
Deji, there is a question from Shyam. He would like to know, what is the switching speed of these switches?
The switching speed is less than 500 picosecond. So we don't know what the ultimate switching speed is. We just use the shortest pulse we've used to switch it is 500 picosecond. So we say the speed is less than. Okay. And we've done, again, this communication engineering aspects of the research. We've done, communication. You can send modulated signals across this nanoscale atomic device. Initially, in our initial publication just a few months ago, we're able to achieve 8.5 gigabit per second, which is on the high end of the 5G requirements. In our most recent measurements, which I mentioned just a few slides ago, we're now getting 100 gigabit per second. That's kind of a record breaking for an electronic device. Typically, to get this kind of 100 gigabit per second, some of you will recall, you have to use fiber optics or optical method. So these are purely electrical devices, and we're getting like optical type modulation speeds. I'll skip this. So let me summarize. I've really spent most of my time talking about MOS2 and HBN as materials in the 2D space for this emerging idea of resistance switching, both volatile and non-volatile for memory. But there's actually a wide combination of transitional metals with the chalcogens that remain to be explored. So if there are those in the audience, perhaps students looking for topics of research where you can contribute fundamental in terms of science and innovation, I would strongly encourage you to consider this. So the properties of these materials are you can get very good on-off ratios, orders of magnitude, even though they're less than a nanometer insulating barrier. Voltages are very, very low, energies are low, it can endure for a long time, can be cycled, and we just need to improve the reliability. So this is what the industry, every time they call me on the phone, they keep asking, when is it mature enough for commercialization? And unfortunately, it's not, because we need to make sure it's much more reliable. And this is kind of the most difficult research to do in an academic lab. Its reliability is more industrial level effort. In terms of the overall memory space, I've actually, to some extent, shortchanged you. I I only talked about one particular instance. This is the emergent memory, so-called atomristos. This figure D of this slide, but there are actually many opportunities that have been explored with 2D materials to improve memory, including 3D RRAM. Graphene is used to concentrate heat in phase change memory. Graphene is used as a floating gate in flash memory. You could use them in take advantage of the spin properties with ferroelectric configuration and this so-called 3-terminal MEM transistor. So there's, again, a very broad space beyond what I've mentioned that may interest others looking for exciting physics or engineering. So with that, I would like to conclude, as I was telling Julia earlier, my main job now is a PowerPoint researcher. The actual research was done by students going to the lab. So I'm very grateful to them. And my postdoc that I told you is an expert on STM really was able to elucidate the mechanism that for so long troubled us and our esteemed collaborators across the world. So I mentioned that I skipped a lot of details. So actually this pandemic time has been very fruitful in terms of publications. Suddenly all our results that we're sitting on for a long time, we just said, well, since we have nothing to do, let's polish them up and submit them. And it turned out that, you know, they were actually good results. So we got a lot of papers out in just this year. So I'll be able to answer any question now.